Alright, so finally time to make this video. The 2023 competition season is over for us, so I figured I would explain how our code works. I'm only doing one take because simply put, this is going to be a very long video and I don't want to redo any part of it. So first of all, when you go into your driver station, some things that need to be configured. Team number needs to be set, dashboard type needs to be set to lab view. Certain parts won't work if you don't do this. Also, make sure you have your USBs in the correct order, with 0 being drive and 1 being operate. This code is designed to work where the triggers are buttons, and like this is 0, 1, 2, 3. So if it's not working on your controller, make sure check in driver station that the triggers are buttons and are not other joysticks. All right. Let's just hop right into it. You always need to open up robot main before everything else opens. You can do it in a different order, it just makes the most sense. So under robot main, you're going to hit Control E. Let's take a look at begin. Now, begin is where a lot happens. So first of all, you'll see feedback configuration right here, analog only, max pressure, and minimum pressure. That is being set to the compressor right here. Here's feedback configuration. We're doing that to make sure that the compressor actually knows that's using an analog sensor. The default is digital. And without this, the compressor just straight up won't run. So keep in mind, our robot's using an analog sensor. If you're using a digital sensor, your code will change. Next, we are opening up two joysticks. And zeroing the yaw on our navx, because the navx starts calculating as soon as the robot's turned off. But we want it to zero once the code's loaded, just in case it drifted at all between when we turn on the robot and when it's fully set up on the field. This helps account for that. And then we are opening up a new solenoid. We are using double solenoids, so it will have 3 and 0 as its as the two channels it's using, and it is on CAN ID 16. Compressor is also on CAN ID 16, so that's what that 16 is. We can ignore the distance sensor that ended up not being used. Oh, this is important. In order for our dashboard to be able to select our autonomous, we need to tell it what autonomous we have. So this is an array. Our autonomouses that we have are plot pursuit, alternative 2, balance, balance cube, and if we were using competition code, which this is not because I don't have access to it, it would be balance cube no M being no mobility. So here we are initializing all the motors and we're setting ref nums to them. A ref num's sort of like a pointer. So then anytime we talk to the ref num, it points back at the motor. So in other words, we can always find the motor from the ref num and change values based off that. So we are setting a current limit of 60 amps. Shouldn't be going above 60 amps. These are the steering motors. They're probably not even going to go above 10 if we're using them correctly. And then we're also opening up our encoders. Now their ref nums look a bit different. All motor ref nums are these yellow ones. CTRE products like to have their own looking ref num file, but it works exactly the same as the yellow ones. You can use the yellow ones in their place. So keep that in mind if you are using ctre products, if anyone's copying this code, which please do, then you would go through and you would delete all this, basically, put the ctre stuff, but you'd keep all these. Encoders are ctre CAN coders. They are the CAN coder V version H, made for the Swarf Drive Specialties modules. And these are the arm motors. So we have arm right and arm left, and then spool. Arm right and arm left spin opposite directions in order to move the arm. So one needs to be false, one needs to be true. Also set their current limits to 60. I just set every motor's limit to 60, which is honestly a really high limit, but we never had a brownout. I was planning on changing the limits if we did. And you'll notice with all these, we're saying they're output to 0 for velocity. That's because as soon as the code runs, it's expecting some sort of command. And since we're not, the traditional approach is a subsystem, but that this code is more complicated and wouldn't quite work with the subsystem approach. So it's got a bit of hard coding in it, and part of that is making sure everything goes to 0 at the start, because otherwise it can go crazy. It can just start spinning. That's not good. And then they're setting the LEDs. In order to use the LED, we're using a blinken. Blinkens are controlled by using the spark motor PWM control. Strangely, it's weird. So we're saying it to PWM 0. The number that you send the blinken controls the LED pattern. We actually don't need this bit right here. What we do need is this 1 to 6.12. You can get that from the box of the Swerve Drive Specialties modules. It's because we're using L2 modules. They are 1 to 6.12. And that is the conversion factor. We're setting it using that one number all these times. We're setting their sensor position to 0 and smart current limit to 60 over here. False, true, false, true. These are the drive marks. So these ones don't try and spin immediately right off the bat, so I don't need to set them to 0. So because the way we have all our motors set up is that all of the bevel gears are pointing left. Yeah, they're all pointing left at the start. We don't have any code that zeros them on the start because I've heard reports of CAN coders either not accurately holding their measurement from power cycles or straight up deleting what they thought was 0. And we wanted consistency, so I viewed it as it's like 2 seconds on the field just to align all the modules. And if it saves us a chance of possibly having a broken match, I'm all for it. So let's begin. You'll notice that we zeroed the navx, but we didn't actually initialize it. Strangely enough, the navx is initialized in RobotMe. Why? I have no clue. Someone was probably not thinking very well, and they designed this library. No, the navx library is great. It does have one slight issue. When using a USB controlled navx, which we plugged into our navx micro over USB. If you use the default polling rate, it will strangely accumulate a lag. The default is 50. In order to counteract this lag, you need to move it higher to 100. Usually, you'd think making it. When I first thought of it, I thought if anything, making it lower would fix it because it had a buffer and it had to get through all the different data before it could get to the next one. But no, strangely, increasing the hertz makes it work faster. It's funny because our robot is named Hertz. Oh, another quick thing. I'm going to close this. If we go to Git FRC 2023 robot project, there's currently an issue with the trajectory library, which you can see I am using somewhere in here. If you scroll through all of it, I'm referencing the trajectory libraries. Those are made by Jim Simpson on GitHub. They're amazing libraries. I'm using an older version of them because that's what our codes are working with, which have a slight issue. So every now and then, when you open, it'll show a cReo instead of a RoboReo. This happens after running code. That's because this 76F2 here, right here, I'm trying to get my mouse to do a thing. There we go. The 76F2 changes to 7AEE, which is code for cReo. So you just need to change it to 76F2. Close the program, reopen it. Do not save anything if that happens. All right. So that's initializing everything. Let's get on to the big thing. Actually, no. Let's go to global variables. So we have this robot takes a lot of variables, like a lot. So global variables, much like a global variable in Java, are variables that can be accessed anywhere within the code. You do this by copying the global variable file and pasting it, and you can create a new one. If you go to structures, global variable, you'll see global one just showed up there. You hit escape. I don't actually want a new one. That's how you create them. They look like another VI. We have 2 of them here, ARM set points and robot global data. I split up because it was getting complicated at the end. So, enable vision, image size, and robot mode are all default. global variables. Don't touch them. Especially don't touch robot mode. Do not touch that one. Enable vision image sizes. I don't really see the point of them. Next, you'll see we have target location. This is used in our autonomous. This is telling us what location we want to go to. Target angle does the same thing. We have LED code, which is that's what we want our LEDs to be set to. -1 is like the really fast RGB mode, so that's what our default is because it looks cool. Auto enabled is a variable that I made that lets us know if our autonomous is enabled, so that way we can switch up what code's running. Smart auto is used later on in the code. We'll get to that. Here are our set points for this is what angle we want each module to be at. This is an angle from, if I'm correct, -180 to 180. So they're all at 0, front left, front right, back left, back right. Here's our current location that we know from our odometry, which our odometry needs to be set here. Again, I'll explain that later. Code this a while ago. This is for one wheel pivot. We don't actually have one wheel pivot implemented, but the file is still in the code. So if you, I think it is, you want to access it, it's there. It's just not actually coded in. And then this navx auto mode and normal. So our odometry always needs the normal navx code or else it won't work. But sometimes our robot's facing the nodes and sometimes it's not. So auto mode is actually kind of our normal. So auto mode is controlled via a variable in the dashboard that will say whether we are facing the nodes or whether we aren't. So it'll either be normal plus 180 or just equal to normal. But no matter what, our odometry needs the normal. Kinematics, these honestly don't need to be a global variable. I'm just saving them for later. PID, proportion, integral, derivative. You're going to hear that a lot. Basically, all of our loops in here are P loops or PF loops. I've tried adding integrals and derivatives, but frankly, they haven't mattered. So every loop that a robot uses is a P loop. And this value was found both empirically and ideal. So it started out with a number relatively close to that, which was calculated gear ratio. And then I just kept increasing, decreasing till it worked really well. Found that despite the slight differences in gears, lithium grease motor or motor batch, they all still work the best with the exact same p-value. But if one of them's not working, here it is. Here's PID. You can change it real quick. You can change it while the code's running. Down here is all our encoders. These values you're seeing are values from when I last ran the code, by the way. So the encoders can get very high. They are continuous, meaning when you rotate past 360 degrees, instead of going back to 0, it goes to 361, 362, and so on and so forth. That's actually very good. We want continuous control. It makes our code smoother. It's kind of one of the issues I'm running into in one of our older code. But that's some of our global variables. Arm set points is just our arm position and spool. Arm position is a value from 0 to -30, and spool is a value from 0 to 210. For the arm, 0 is all the way up, -30 is down. In other words, it's 3 degrees per number. And for a spool, 0 is all the way in, 210 is all the way out. All right. Now, the big thing. Periodic tasks. Periodic tasks also stores the arm PID and spool PID. You'll see the arm has this thing called a feed forward value. So what P works is basically the way the P works in PID is you basically take how much you are off and you divide that by the P value, and that's how much speed the motor is going to get. Feed forward is like a slight constant push, where if it's not quite there yet, it gives it some output value. So in this point, the arm almost always has a value of 0.4. The arm never goes faster than 0.3 or -0.3 because, simply put, at those speeds, it's fast. Imagine how fast it would be higher. Here's our position X and Y, our LED code. This was used for debugging. This is our yaw, roll, pitch, heading, and fuse heading. You can ignore heading and fuse heading. They're not going to be accurate on navx that's surrounded by neos. Motors make it inaccurate. I'm just going to double check that I am recording because I've been talking for a while. All right, I'm recording. So let's start at the top. Being honest, these values probably need to be changed. Our swerve drive kinematics. This is basically telling our robot or telling the code the location of every module. In meters is not accurate. Our robot drivetrain is actually 25 by or yeah 25 by 25 without bumpers. So that's what this would be need. This would need to be changed to 25 convert to meters divided by 2, and then negatives and positives stay the same. But either way, it's translating to a translate 2D point, which is their own thing that WPI uses. All this, every block that looks like this, is actually code that used to be part of the Java, or that's part of the Java WPI library. But again, Jim Simpson converted it all because he's awesome, and led to us being able to use the Java code in LabVIEW. It's over, I think, over 100 files. Really great work. Anyways, so what this is doing is this is setting up all our modules, sending them to creating new swerve kinematics. That's where I send it to global data. Oh, we actually do need it. So then our swerve, it's, oh no, it goes, sorry, I coded this weird. This wire goes down and up into swerve kinematics on our swerve odometry update block. This thing is basically the giant math handler. It handles all the math. Here's us creating new swerve odometry where you see a coder, everything set to 0. And that's our initial position. And our initial positions here, x of 0, y of 0, degrees of 0. And our initial module position is right here. Our gyro angle in degrees is going into gyro. It converts into this weird thing. You'll see anytime we're using an angle, we're actually using its radian, cosine, and sine. It's just built in there because it makes it, I guess it makes it easier for converting later on. Then rotate at angle block. That's getting our navx from normal. Again, I mentioned that earlier. Here's where we get all our encoders. First of all, we send them all to the network tables, which is sort of like, what's this thing doing in here? Oh well. I'm going to delete that. Our network tables is sort of like how everything talks to each other over Ethernet or Wi-Fi. So in that case, if we want to talk to a robot, not through just joystick commands, then the way we talk to it is via network tables and a dashboard. So this is telling our dashboard that all of our where all of our encoder positions are. It makes it very helpful to see if something breaks. It's also telling us if our navx is working. System status. That saved us that's helped us in competitions. Here's all of our drive motors. We are getting all their sensor positions. Remember how we did that neat conversion thing where we're getting it here. This was used for something else. But remember how we did that neat thing where we set the conversion value to 6.12? Well, here's where it's used for. In every single swerve module, it's swerve module position new. So this is saying that there's a new position for the swerve module. We're sending it its angle through our encoders, and we're sending it its how many times it's rotated or what rotation it's at in in feet to the distance. And then we're sending that all to the swerve odometry update. Now, for some reason, the Java library likes to use y is left right and x is forward backwards, which seems really backwards in my mind. So also one of the values was inverse, so I inverted that, flipped it around. Also, yeah, one of the mentions was that you may need to invert the gyro when putting the example code. So yeah, I did in fact need to invert the gyro. Ignore the stuff I was writing. So then we're setting our current location variable right here. It's all in a 20 millisecond update loop. Any faster than that and the code will probably crash. Here is more network table stuff, just telling it CAN bus information. Here's where we're setting our yaw offset. So here's how you read from network table. You nt read boolean, default value is true. It's called yaw offset. So at false, it's 0. That means there's no offset. At true, there's an offset of 180. And that's just sending it to the navx variable. And it's also writing our recalculated yaw to network tables because we want to use whatever our recalculated one is. So odometry, it's scary, but if you just use the library like this, just have each module. I also need to invert some of the distances. Kind of weird. Coincidentally, I'm pretty sure it's the same modules I need to invert their rotation. Yeah, kind of just guess and check till it works. Oh, also, this was something that meant to be included in the code, but wasn't, but now it is. So we're using our swerve odometry also as an initializer for this feedback loop. Feedback loops, or feedback node. Feedback nodes, when placed in a loop, store data from the last iteration of the loop, and then give it back. So, obviously, for our odometry, we need to know where we were to know where we are. So this is telling us where we were into our in swerve odometry. And then, so that way it has where we were, now it knows where we are. Without this, it'll just, after you stop moving, it'll go back down to 0, which is not ideal. This right here is just a fancy for loop. You honestly could have, I didn't want to do as 4 individual ones, so instead of spending the 3 minutes to make it 4 individual ones, I spent the 10 minutes to make it a fancy for loop. Down here. So I made a bit of an odd choice, which honestly helped us in splitting up a lot of motor control to being under periodic tasks instead of under teleop and autonomous. So here's setting the encoders to a global variable. Here's control of all of the modules. So modules, right here, this is the PID maximum and minimum, maximum being 1, minimum being -1 because it's using percent VBus. In other words, 1 is 100% speed, -1 is 100% speed in reverse. In our PID block right here, here's what the PID block looks. We have our set point, process variable, or process variable is or that's our feedback, that's our sensor. In any PID loop, process variable is the sensor. Then we have our PID gains, which again, that's stored in the PID global variable. And then of course our output range. DT should always be, I think, -1's the default. That means it happens at a 1 millisecond loop, which is what we want. We send our output, we get our data from our ref num. Remember how we said it earlier? Now we're getting it. So now we're getting our data from our ref num, sending our output to that, sharing a variable. Now what's this thing right here? It says, you can't see it, but it says smart plus. It has our x, our y, and our old x. This math is courtesy of Nathan. And what it basically does is, so since our sensors are continuous, if we were to be rotating our module, and so it's rotate around, it's at 359, and we want it to go to 90 degrees. It's not using a continuous control, it'll flip all the way around, which is obviously not ideal in the best way. It's just to go like that. So what this math is doing is this is basically saying instead of going to 90 degrees, it would go to 450 degrees. It's doing a bit of math, figuring out some difference, and it needs to get our previous data. Originally, I had something where if it was equal to 0, it was having an issue with going equal to 0. So quick note, the feedback node cannot be placed inside this block. If you place it inside this block, it breaks. So that is why feedback node is here. Default is 0 for initialization, which already helps us because that's what we want our default set point to be, and our default position. And what's this thing over here? Converting something to radians and doing all this math? So actually, let's just talk about this real quick. This right here. This is our arm. This is how we code our arm. We have arm left and we have arm right. Here's our arm output variable, PID. It's organized weird, but it's basically the same as any of these, where it's just You get your feedback, except this PID is slightly cooler because this PID has a feed forward value. This one does not. There's no feed forward down here. There's feed forward down here. This is because this is parallel PID. Well, this is just normal PID. Parallel PID can do feed forward, although it takes more math, so that's why we're not using it here. We're again setting our output. You see this time its maximum is 0.3 and negative 0.3 because we don't want our arm to be moving it faster than 30%, or else it will break something or kill something. It is scary how fast that thing is. And we have, again, we're calling our ref nums. It's a lot of a repeat. What we're doing right here is we're getting our sensor position, multiplying it by 3, and then adding it with 90 to get. That's when you do that. That's how you get our arm angle. So this is 0. This is 90 degrees. And then now it's convert to degrees. We're using that convert to radian thing. Getting our radians because LabVIEW is cosine takes radians only. Cosine of that divide by 62 because there's a limit. You can't extend past 4 feet outside your perimeter. So 62 is the maximum extension from the pivot point of our arm to 4 feet out. It's basically, I did cosine theta times hypotenuse equals like the extension. So, oh no, 62c the length of our arm. No, can't remember how I did it. Okay, I'm tired. Point is, what's doing here is then, as long as it's not further than 46.25, or subtracting 46.25, why did I choose this number, 46.25? That is that's a maximum we can, or no, I know what it is. 46.25 is, the distance that our arm can extend. No, the distance our arm can't extend from the maximum extension. So fully extended, that's a distance that's not being used. If the arm's not extending enough, make this value smaller. If it's extending too much, make this value bigger. Make sure the arm's always at 0 at the start. And it's doing that if it's equal to 0, no, absolute value of that, because sometimes it would give negative degrees, that would throw everything off. If the absolute value of that is less than what the arm's current position is, which is getting that current position thing from here again, 27 divided by 210, that is the extension of our arm, because our arm can extend 27 inches, and 210 is the extension of the what's called is 0 to 1, or 0 to maximum for the set point. So that's kind of converting it to inches. So if that convert to inches multiplied by here's the sensor position for the spool. This is for this extension. If that is less than this, or no, if that's greater than this, it'll set it equal to the maximum extension possible. Not possible, maximum extension allowed within the rules. Otherwise, it just lets it do its thing. Multiple inspectors have checked over this code and can confirm it works. Because every time they're like, well, can your arm extend past 4 feet? I'm like, well, yeah, I can. They're like, okay, well, isn't that against the rules? I'm like, well, yeah, but it doesn't. So here we're getting that global variable LED code. We're displaying it as well. And here is where we go back there. Here's where we set it equal to motor output, the SparkMax, again, getting the ref num. Here's spool PID. Oh, spool doesn't use PID like normal. So I actually don't need the spool PID right here. I could delete this for all I want. But the PID is built into the SparkMax because there's no feed forward, and SparkMax can actually do feed forward. It's just I don't trust it to handle the ARM code because I don't want to type in something wrong and break the ARM. Since I have one of them inverted, I don't know how it would work. But we're just saying it equal to the position mode. Position uses SparkMax built-in PID. Remember the smart auto things I was talking about? Here's what they're for. This is the quote-unquote auto-enabled dumb auto. So you'll see it's getting a bunch of values. What's getting is the set points and the positions. And if the set point and the position are within 0.5 here, this is the who cares variable, or it's actually called smart comparison. Set point process, who cares index, and if it's happy. It's happy if the two variables are within their who cares index. So for the arm itself, that's within 0.5. For the extension, that's within 1. And if it is, it sends a value, it uses an array, sends a value to one-shot pulse to next point. So normally in LabVIEW, this would do is it would set true until the next set point is set, and then it would be inaccurate. But that would take too long, and that would actually skip through all of our set points in auto. So what this does is it actually just straight up it sends a value once. So it'll go if it's true and then false, or no, if it's false and then true for 1 second, and then back to false. This will only send true for 1 millisecond. It'll send a 1 millisecond pulse, one-shot pulse. The block's image actually does a good job at representing that because it goes from false to true for a while, and this is just one pulse. It's fairly simple how it works. It's just a little bit of code, feedback node. But yeah, for using a smart, also 1 millisecond loop time. I use a lot of things in 1 millisecond loop. This whole thing is a 1 millisecond loop. Why 1 millisecond? That's what teleops loop is. So motor control is expecting data in a 1 millisecond loop, so keep it up. Here's the smart auto. Also, here's no auto. Auto disabled, but smart auto, you can see, a bit more complicated. So this is basically a hard code version of the who cares index, where if it's in range. So what this is doing right here is if every single thing in this element is close enough, if our degree is within 5 degrees, if our arm is within 0.5, if our arm extension is within 1. And the way this works is these are a bunch of PID loops. So go to point, the file that is target location, current location, and 2 PID loops, an X loop and a Y loop, which do have to be different. And were manually tuned, involving a freshman getting hit by the robot briefly, and he was okay. But these are sending values, and when the values they're sending start being less than 0.1, then that means it's good. So that's for go to point, and go to angle, as you can imagine, is very similar, except it has some things to handle if the angle is equal to 0, because the way the navx works, the navx gets kind of funky when you pass by 0. So it's got a bit to handle that. And it's sending all these values to swerve M for auto, swerve drive immediate for auto, which is a copy of teleop stripped down to just the drive code. We have our swerve math, we're setting all our set points, and setting all of our drive motors. I don't know what this is here for. Little funky thing. But point is, then again, it goes to next point. So what that next point used for? Well, let's take a look at auto. So first of all, let's go through the blocks. We've got auto align. This gets a target data and just uses a PID loop to control our rotation. I'm not going to go into autonomous independent. URSL go to point and go to angle. Drive for time. This just runs the motors for a set time and it uninverts the two that are inverted. And because we were having drift, I had to actually multiply half the motors by 0.87 to make it drive straight. Autonomous independent. All right. Where's the default? Default is nothing. This is what happens if there's no auto. We get joystick values, but why would we want joystick values? Why? Hold on. That makes no sense. Okay. Someone at LabVIEW is making no sense because the auto can have joystick values. Oh wait, no, that's for 2019 when you could actually control the robot during auto. So let's go to the simplest of them all. Alternative 2. This is the simplest. So what this is going to do is, first of all, it's going to enable Smart Auto. Auto gets enabled automatically. It's going to set to Smart Auto twice just so that we're sure. Give a 40 millisecond wait so that way it has time to set. Next, it's going to take our arm set point. And if our arm set point can go up by 3 and not go, or if it can go up by 3 and then it will, and it'll set that to our arm set point. Our spool is the same. So basically, that's going to tell our arm to move to, I guess, 9 degrees above where it's actually supposed to go to. So that way, if it's holding an item, it would go to like here, and then it sets it to what it's supposed to be, where it then goes down and drops it. That's just how our arm works. But you'll see after each setting, there's next point. So that means it's going to run until it gets to the next, until it's close enough, which is again the who cares index tells it to go to the next point. So it moves on to the next point, where then it sets the arm position to where it should be. And that's good. It moves on to the next point, gives it 1 second of time to wait for it to make sure it's really in that point. Then it opens up the claw, waits a tiny bit, because if we stop immediately, it's an issue. Sets the arm position to 0, and you'll notice it's not waiting for next point after setting the arm position to 0 and spool, because then it's going to start driving backwards. And right here is our timed delay, our drive for time, D for T. LabVIEW time delays suck. LabVIEW timing sucks. You cannot just say start the motors and wait for a set point. That will stop all code. I don't know who designed this. This code right here is code from the WPI library autonomous wait thing, but I stripped it down and put it in here because it only works if it's actually in the autonomous independent file. So it tells it to go for its drive for time speed, which it gets from network tables, drives for that time, sets to 0. On enabled, gets set to false. Honestly, 1712, make sure you switch to Java so you don't have to deal with this pain. This was coded during lunch at a competition. Alright, let's go to the next easiest, balance. So what it does is it gets the pitch, and as long as the pitch isn't 10 or negative 10, it'll drive backwards. Because at 10 or negative 10, that's when we start going on the ramp, to which it slows down a bit until we go over it once. So then once we're over it once, then it engages in a P loop. So I'm just taking where we want to get to 0, so I'm just taking the pitch, dividing it by negative 0.01, and setting that to our drive for time. And then once it's close enough to 0, which is 2.5 or negative 2.5, or in other words, what the scoring counts as a balance, it'll set to stop moving. And if that doesn't happen, it'll set to stop moving at the end anyways. So if you noticed in the competition, our score 1 balance stopped working, which that was balance cube no m, actually, so it was a different version of this. That's because after falling, our arm was we don't actually know what the issue is, but my hypothesis is after falling, our arm was shaking. And because of that, it would shake, the robot would actually tip forwards and then backwards because it rushes the arm back up in order to make sure it has time to do everything. So, during that time while it rushes the arm up, it would tip and throw off the navx. So you'll see right here, this code in the first sequence, flat sequences, which by the way, I should have explained what these are. These execute one thing after another. So it'll do this, then this, then this, then this, once each one's done running. So our first bit in the flat sequence is, we set everything equal to 0. And then we actually, this is the exact code from alternative 2 with the weights removed. Because we're just doing a cube, we don't have time to wait. Then you'll notice it used to be negative 0.3, now it's positive 0.3 because it rushes backwards. But that has to go slowly over the switch because now we're heavy sides on our back. So if we go too fast over the switch, we'll tip and fall. And falling is not good. Waits a tiny bit. And then, so this is it then after it tips the switch, drives backwards at a faster speed. This actually got changed to 0.7, 70% speed. Zooms off the switch. Drives back up at a fast speed till it tips the switch and then engages the P loop again. And then once it's good, it changes, or once it's balanced, it's balanced. So it scores 1, drives backwards, drives forwards, and balances. Although, again, stopped working. Plot pursuit. This code. Is this the stripped down version? This is a stripped down version. It used to have all these network table things that don't matter anymore. So we tell it auto enabled, and smart auto is false, strangely. Oh yeah, because at the start we don't want smart auto, so it runs through the alternative 2 thing again, the alternative 2 sequence. But here's where it changes. It goes. I actually need to change this. It goes to the first point. So now we will tell it to go until run next point until target location and target angle are where we want. It also sets the arm and spool to 0. And then waits a tiny bit. Here used to be a lot of code. Then it does it again. Except there's x1, y1, and x2, y2. Now is a good time to bring in the dashboard. If you go to the dashboard, you have x1, x2, y1, y2. True, facing nodes, false, not. So that's our, here's all of our data we're getting. Auto delay. This is not needed. 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 This is not. All that's needed is mobility D. Mobility D is telling us our time to drive for any time we're using alternative 2. This tells us how long we need to drive in alternative 2, so change the time based off where we are. This tells us our speed. Negative is if negative actually moves us forwards, positive moves us backwards. Basic arm, so if we were scoring high, we would do -15 and 210. Those are the values you want for scoring. And then our points. These are in feet. So this is where we'd want us to drive to. And then you select your auto here. When we actually have network tables, it shows up there. Don't save. I want to reopen that, but without all that tinkering. Here's what it looks like. Here's just it's under custom default. You can find it if you place something under custom and then like here, and you just double click on it. It brings you to where it is in the code. So here it is, just a ton of setting and a ton of reading. It's repetitive. You see x1 goes to x1, y1, y1, x2, x2, y2, y2. It's very boring. There's nothing you need to know about this. Dashboard is, other than that, it's a default dashboard project. Oh yeah, press this to record, this to stop. So doing that actually saves it to this PC, users, public, public documents, FRC, log files, dashboard, which is the most recent, this one. You can actually watch a video of a robot moving. Ignore my, that's my fan control, or my temperature software. You can actually see it drives up. And I don't know the bandwidth this takes up. So see, this is our auto align working right now. It locks onto that target that it sees. That this is the Limelight's point of view. It sees that target. That's why it's putting a plus over it. We place it there. Yeah, so that's what you need to know about the dashboard. Dashboard can go away. I think that's it for auto routines. Yeah, that's it. Okay. So I can close that now. Good. Anything important? Oh yeah. Some other things to remember in Finish. You need to close the compressor and the joystick. You don't need the joystick, but you do need to tell the compressor to stop. I can close periodic tasks. Finish. Now the reason why some other teams might be looking at this horrible video. Teleop. Oh god. So in order to avoid tipping, let's go up to this. I'm using a block called rate limiter. This block is available in the Dogma programming library, which is found on our GitHub. it takes a max derivative, an input value. I don't use starting value or reset. So input, output, max derivative. Our max derivative is 5, meaning it takes 0.2 seconds for the, or it has to take at least 0.2 seconds for us to go 0 to 100 or 100 to 0. This stops us from tipping pretty well, or it stops us from tipping over. Gets us close to tipping over, but not there. Here's reading data from the Limelight. We didn't end up using it in the competition. This is slow mode. So you'll see something that looks like this, some form of this, a lot in our code. I call it the T flip-flop. If any of you ever play Minecraft, you'll know what that means. So when this gets a one-shot pulse input, it'll check slow mode, which is a local variable. Local variables are these things right here. That's local, that's local. Any front panel item is a local variable by default. So also you see I set auto enabled to false because we're not an auto. So what this is doing right here is check slow mode. If slow mode is true, sets it to false. If it's false, sets it to true. Basic code. Also sets our target location that was used in debugging. Field-centric mode works similar. You'll see down here, here's the field-centric, here's stop mode. This is just how I control things. And when stop mode happens, so does LED. So does LED mode being set to -1, which makes this go that makes the LEDs go into party mode. Here's the very first version of that code, which is a Limelight. It's for the Limelight. Made it so when I pressed the A button on the controller, it would change the LED pattern. For any freshmen trying to drive the robot, here's what you need to know about. Got an Xbox controller right by me. I don't know if this will show up in the video. Slow mode. That's it. All right, that's all you need to know for controls. Also, one of the two small buttons is lock mode. The other one doesn't do anything, so don't worry about hitting it. Here's getting all the buttons for the joystick. I use just about all of them somewhere in some point. But the only button you should hit is slow. It's a trigger. When you hold it down, it puts it into slow mode. I think it used to be no, stop. It's not. It's something. Here's our auto align code. I named it meth because I was tired that day. That's auto align v3. But the real question, how did we get Swerve Drive working in LabVIEW? We stole the code. More or less. Modified it. So here it is, Swerve Math. If I remember correctly, this is from Team Cherry Pie, or Apple Pie, the one that made the whole presentation on how to use Swerve Drive in LabVIEW, including odometry. This is their code. I mean, it's made from their presentation. So is it really stealing code? We're saying our track width and wheelbase to 23. As long as they're both the same number, it doesn't. If you're using a square, you could set it to 1. You could set it to 20. It doesn't matter. What does matter is if you're not using a square, you need to change those numbers. We've got our gyro angle, which is our yaw is being put somewhere. What these things are doing right here, the saying it equal to 0, is if the value is close to 0.1 or -0.1, or if it's in between 0.1 and -0.1, it just sends 0 instead because that will account for any stick drift or anything like that you have. And here are all of our outputs, which it explains in the blog. WSWA, front right, front left, all that. Here's the actual math. Does it say the team number in it? No. If you want to knock yourself out, or if you want to read all this code, knock yourself out. But yeah, here's the Swerve Drive math. It's also labeled. And then we are setting all the angles equal to their set points. Although, strangely enough, I found that I think it was front left and front right angles needed to be swapped. I don't know why that is. And saying the speed equals the speed. And here's slow mode. You see if the trigger that's over here that equals slow mode, if one of these, if we trace the wire back, which I'm not going to, if it's true, it's 0.3. If it's false, it's 0. Or if it's false, it's just full speed. We were driving at full speed most of the competition. If you watch recordings of us, it's pretty clear that we were. And here's our PID, which, because I used to need all these, I don't anymore. I should probably clean up the code at some point. So, even more of that flop thing. This is for cube mode or cube mode. True is cube, false is cone, default is cone. Also for claw. So you'll see the claw is just equal claw here. True is forward, false is reverse. That's what this thing does right here. It's again one of those flops. Here's a bunch of one-shot pulses that would work if we were using the distance sensor, but we aren't, so it just does nothing. Some math made by Aaron. Pretty cool math. Anyways, here's all of the buttons. So first of all, if we're pushing a joystick value, and again, it's within that certain range, then what we are going to do is we're going to steadily increase the set point or decrease the set point. And that increase or decrease is scaled based off of how hard you're pushing the joystick. So that way, I'm pretty sure left is moving the arm down and up, and right is moving the arm in and out. Here's the ground preset. It stays the same throughout all of them. Same with stowed and substation. Those are all achieved by pressing buttons. Now here's cone, mid, and high. Cube, mid, and high. And cube mode also controls if the LEDs go yellow or purple. Because when we switch between the two, that's how we let our human player know where we're going. All in all, it's a lot of code. I honestly thought it would take a lot more time to explain. If you have any questions, comment them on the YouTube video when this is uploaded. You can take a look at Swerve stuff, see if there's anything I missed. Yeah, I'll tell you how some other stuff works while I'm at it. Hold position. So it sets all of the motors to hold the position 0, and then sets the set points to be pointing, making an X. So the robot's not going anywhere. Real simple. Rotate around module. Handy dandy table that I made right there. So there's 4 different cases: 0, 1, 2, and 3. Again, here's the table. This says this will only work with a square robot because I didn't do the math for if it's not a square. And it sets it sets the rotation speed equal to different numbers. And while so in order to rotate around a module, you set the module you're rotating around equal to your navx. So that way, as the robot rotates, it stays still, or actually equal to the inverse of the navx. Then you set the other two modules like this, and the last one like this, because they're all equal to the tangent of the angle. So tangent of 0, straight up, undefined. Tangent of 90, flat, 1, or I guess 0. Tangent of 45 degrees, that would equal -1. But because this module is further away, these are all distance 1 away, these are all distance 1. This is distance 1 root 2, if I remember correctly. Yeah. So due to that, we need to make this one needs to be spinning the fastest. So the other ones get divided by root 2. And that's what this part right here is doing. I don't know if my hand signs will show up. I hope they will. And that's putting of course, one of the speeds equal to 0 in the module, it's not moving, and here's all the angles: 45, 90, -90, 0. See that down there. Yeah, that's how rotate around one module works. That deferred decision. Any other things? Should reverse. If you are using swerve modules that cannot rotate full 360s for any reason, say your motor is located on the wheel, there's a swerve should reverse. It's included in swerve post, which is maybe under dependencies. I don't even know. I don't use it anywhere. It came with part of the code I was using. Yeah, that's basically it for that. That's it. All right. I'll watch 10 hours as this video uploads to YouTube. Good luck, future Dogma members. Hopefully you switch to Java. To any teams crazy enough to still be using LabVIEW, I respect you and I'm slightly afraid of you. A lot of the odometry code was actually coded in an all-nighter. Um, all right. Contact me if you have any questions. I'm going to link the GitHub repository in the description.